Thank you so much. So I'm going to talk about an auction design for a behaviorally biased type of agent that we call cursed agent. So this is joint work with Alon and Juntao Wang. Let me start with the famous wallet game. So suppose that there is a wallet and we have two players, Alice and Bob, each privately contributing to some amount to the wallet. So the prior distribution for their contribution are all from a uniform distribution between 0 and 100. And each know their own contribution and they don't know the other's contribution. And suppose we're going to auctioning off this wallet that contains the sum of their total contributions and ask using a second price auction. And we can ask the question of, oh, what are the reasonable strategies for players to bid in this auction? So suppose Bob actually has a private realization of his contribution B that equals to $30. And Bob might reason that, oh, since the prior distribution for A is a uniform distribution between 0 and 100, so the expected value of Alice's contribution A is $50. So I can bid the summation of $50 plus my own contribution, $30, which is $80. So this is a natural strategy. I'm not saying that this is a rational strategy. This is a natural strategy for Bob to think about participating in this game. And if Alice is using the same strategy, so if we're considering the case that this symmetric strategy scenario, then what Alice would bid in this game is her own contribution A plus the expected contribution of B, which is again $50. And in this case, Bob will win the auction even only if the realization of B is actually greater than or equal to the realization of A. But like, what's wrong in this reasoning? So rational agents would not play such a strategy in the wallet game, but this type of strategy are often observed in practice. So the expectation is not conditioned on the action or the fact that Bob wins the game, so wins the auction. So if we're thinking that conditioning on Bob wins the auction, then it must be the case that Alice's realization A is less than or equal to Bob's realization B, which is $30 here. And then the conditional expected value of A now becomes only $15 instead of $50. So Bob fails to really assessing the expected value of A, conditioning on the fact that if he wins the auction. So these are going to lead to a negative utility for Bob in expectation, because if Bob wins the auction, then the expected value of the money in the wallet is $45, because the conditional expectation of A is $15 plus what Bob has already contributed, which is $30. But the expected payment of Bob in this case is actually $65. So because that's the sum of the conditional value of A plus the $50 that's plus the $50 that Alice added to her bid. So this is the second price auction. So Bob actually loses $20 in expectation if he wins the auction. So rational agents will not participate in this wallet game using the strategy that I just described. But this strategy has been observed in practice, and that is often referred to as the phenomena of the winner's curse. So winner's curse happens usually in interdependent valuation auctions. So that is the value of the item actually depends on everyone's valuation private signal. And the winner often behaviorally overestimates. So the winner has a behavioral bias in participating in the auction. And the winner's curse refers to the fact that the winner often pays more than what the item actually was. So there is some large literature starting winner's curse in auctions. It happens in many real-world auctions, and it has a negative effect. So clearly has a negative effect. One may argue that since this is a behavioral bias of the auction participants, it gives the auctioneer opportunity to exploit such biases and earn more revenue in auctions. So that is definitely correct. But on the other hand, the negative effect of the winner's curse may lead to a winner of the auction into bankruptcy. So if someone wins the auction, but eventually that leads to bankruptcy, that doesn't benefit anyone. It also can lead to the participants to reluctant to participating in future auctions. So that's also not an ideal outcome from a platform's perspective. So Eastern Rabin 2005 paper introduces a behavior model that's termed the cursed equilibrium to try to explain the winner's curse. What we're going to do in this work, what I'm going to focus on talking about in this talk is, can we adopt that model, that behavioral model of the agents, and think about the auction participants are behaviorally biased in a certain way. And then we think about the mechanism design question for this type of agents. So, and then ask, can we design mechanisms with good incentives that avoid the winner's curse? So means that the winner of the auction never gets a negative utility. Okay. So the answer is yes, but certainly it has a cost to the auctioneer. So the seller may have to compensate the bidders. So even if those losers of the auctions needs to be compensated. So we also provide method where the seller can use to achieve good social welfare and revenue, because the seller needs to compensate the bidders. The seller may incur a revenue loss, and we want to prevent that. We allow the seller to explore the trade-off between the social welfare and the revenue. Let me introduce the auction setting that we're talking about. So we're considering a single item auction setting, and there is a set of n agents, each with a private signal Si. And we consider the symmetric setting where the signal distribution is symmetric, which is represented using the density function f, and individual has the valuation function that takes into consideration of not only his own private signal, but also the private signals of other agents. So the valuation function is symmetric. An example of the valuation function could be a linear function that takes the sum of agent i's valuation Si and some scaled version of the sum of all other agents' private signal, Sg. And the valuation function Vi is increasing in all its components. So in its own private signal Si and also in other agents' private signal Sj. Okay, so this is the standard setting that has been considered in the interdependent valuation setting for auctions in the literature. And we consider the direct mechanisms, and agent I submits the base Bi to represent his private signal Si, but the agent I can choose to misreport. And then the mechanism is consist of an allocation rule, which we use the notation Xi, and a payment rule, which we use the notation Pi. And then a utility of agent I is just the difference between the realized value that the agents has if the item is being allocated to that agent and the payment that this agent needs to pay to the auctioneer, to the seller. And the agents needs to decide a bidding strategy, so which is the condition, which is depending on his realization of the signal Si, choose to submit a bid BI. So that's the bidding strategy signal. So let me come to talk about the more formalized version of the behavioral model, because I started the talk by saying that, oh, rational agents will not participate in the volley game as I described, but that behavior has been frequently observed in practice. So the particular behavioral model that we're going to use was proposed by Easter and Rabin. So let's go back to think about the valid game. So in the valid game, what went wrong was because of the agent was not conditioning his expectation on was not conditioning on his expectation on the factor that if he wins the auction. So what it means is that he has a wrong belief. So the agents actually fails to account for the dependency of other agents' action and signal when estimating the utility. So in other words, the agent's belief is wrong, but the agents were able to do best responding according to his belief in the correct way. So that's where the biases comes into play, is the agents was having a wrong belief, but the agents actually can do reasoning based on his belief in a correct way. Okay, so Easter and Rabin captured this phenomena by separating the agent's belief into perceiving this as independent of perceiving this as the other agent's signal being independent from its actions. So the agents was neglecting the contingency between other agents' action and other agents' signal. So let me try to explain what exactly it means. So if the agents were trying to think about the expected utility that he's going to receive from a bid profile B, so other agents are bidding B negative I, and agent I is bidding BI, and agent I has private signal SI, and conditional on a particular strategy profile that other agents are playing. Then what the agents correct reasoning of this expected utility should be, oh, what's the realized utility? And taking the expectation of using the joint distribution of other agents' bid and other agents' signal conditional on agent I's realized signal. So this is the expected utility of agent I after receiving signal SI. And what a fully rational agent would do in terms of thinking about this joint probability distribution is that the fully rational agent will first reason about conditioning on my signal SI, what are other agents' likely signal? So that's the first step. And then the second step is, given the other agent's likely signal S minus I, what's the probability for they're going to bid B negative I? So there is a contingency. So there is a relationship between the other agent's bid and the other agent's signal. And the agents were able to account for that correctly using the Bayesian rule. But what a fully cursed agent is going to do in this model is that the fully cursed agent thinks that the other agents' bids and signals are independent. So even if the fully cursed agents can reason about, given my own signal as I, what's the probability that the other agents are going to have signal as negative I? But this agent is thinking that the other agent's B negative I is independent of the realized signal as negative I. So this term is wrong for a fully cursed agent. And then Eastern Rabin allow agents to be not fully cursed or partially cursed by doing a linear combination of the probability for what a fully rational agents would obtain and the probability of what a fully cursed agent would obtain. So that's essentially assuming that the other agents, B's and signals are independent for the second part. And then this is parameterized using a parameter he here. So the Greek letter he represents the degree of cursedness of the agent. And what they propose is what's called the cursed equilibrium, is saying that, oh, the cursed agents are using a wrong belief when calculating the expected utility. But these cursed agents are doing the best response to using this expected utility. So the cursed expected utility is with the superscript he, and this right probability distribution depending on its degree of cursedness he. Okay. So cursed agents play an equilibrium strategy with respect to this cursed expected utility. But because of the bias is happening with a wrong belief, it is somewhat challenging to think about how can we do mechanism design with cursed behavior agents. But a very nice equivalence results helps us here. That is that a cursed agent who has the wrong belief can behave just equivalently to an agent who has the correct belief, a rational agent who has the correct belief, but has the wrong utility. So this is the behavior equivalence that Eastern Rabin obtained. So the cursed expected utility that has the wrong belief here, but with the correct utility, if I expand the utility, so what's in green is just the utility of the agent, that's the correct utility. This can be equivalently written using the following expression where I have the correct belief, so as if the agent actually is a rational agent, but with a wrong utility. And in particular, the wrong utility can be captured by this wrong valuation function. So this VI he is the valuation function that we call the cursed valuation for a cursed agent. And this valuation function is the linear combination of the correct valuation that the agent should has and the expected valuation where the agent's actually not accounting for the independence. And this is kind of like the combination of these two gives the cursed valuation for the agent. So now that allows us to really think about cursed agents or the cursed equilibrium type of a behavior just as rational agents who overestimate their valuation, who has a cursed valuation function. That makes the idea of thinking about mechanism design for such cursed agents easier. So empirically, what Eastern Rabin found is that almost any positive cursedness parameter he fits the empirical data of the volley game better than the rational agent model. So the fully rational agent model. And a he around 0.6 fits the volley game data the best. So that's typically empirically what we think the he tends to be. Okay, so that's the agent model that we're going to consider. So essentially, we're going to consider the behaviorally biased agent, and the behavior bias is captured by this cursed agent model with a fixed cursed parameter he, and that the value of that parameter is known to the mechanism designer. So now let me turn to the mechanism design problem that we're considering. So we want to design. Yes.
Yes, you have 10 minutes, just to let you know.
I have 10 minutes?
Yeah.
Oh, do I have total 30 minutes or do I have a total of 20 minutes?
30. Am I wrong?
Yeah, I think I may have 20 minutes.
No, you have 30 minutes. In total, you started at 6:18, so...
Oh, okay. Yeah. Okay, yeah, that's good. So
just so that you plan, you know, exactly on what you want to spend.
Yeah,
okay.
Yeah. Thanks. So let me talk about the desired properties that we want to achieve. So we want to achieve exposed incentive compatibility, but for cursed agent. So this is the counterpart to exposed incentive compatibility for fully rational agents. And we also want to achieve exposed individual rationality for cursed agents, just as the counterpart to the exposed individual rationality for rational agents. But on top of that, what we want to add is that the winner never lose money. So we want the exposed IR, exposed incentive compatibility constraint to be satisfied. So the cursed exposed incentive compatibility and the cursed exposed incentive individual rationality are really just analogous to what we would define them for the fully rational agents, except that here we're defining them using the cursed evaluation function of the agents. So that means that the Myerson's lemma generalized by Roughgarden, Talgam, and Cohen for the interdependent valuation setting naturally captures the space of the mechanisms that are cursed exposed IC and IR. So it just requires that the allocation functions to be monotone, and then the payment will satisfy the Myerson's payment identity, but with the cursed evaluation function. But what we need to add is the exposed individual rationality, saying that the winner will never lose money. And that mixes the cursed valuation function with the true valuation function together and makes this to be challenging to analyze. So we turn to this to the restricted setting of only considering the deterministic and anonymous mechanisms, because this set of the mechanisms are optimal when we consider fully rational agents. And then in this setting, the allocation rule is just a threshold function. So when the agents submit a bid that's higher than this threshold, the agent will be allocated the item. So we call this threshold TI, the critical bid of agent I. And then the Myerson's payment identity gives us the cursed exposed IC, and then we also have the cursed exposed IR here. And what we're adding here is the exposed IR. So this is the condition that we're adding. And observing this, all we need to really worrying about in this setting is how to set this PI 0. So because that essentially is saying that how much we need to pay, or the agents needs to pay when the agents submit a bid 0. Okay, and if we take a look at what this means is that if agent I loses, then it gets 0 and it pays something that's non-positive. So the exposed IR is satisfied. And when the agent I wins, it gets a valuation of VI, and it pays according to its cursed valuation plus this PI 0 term. That also satisfies the exposed IR, because this PI0 is non-negative, non-positive, and the cursed valuation is less than the true valuation. So the only scenario that we need to worry about is when the cursed valuation is actually higher than the true valuation. This is when the winner's term curse happens. So this means the curseness will says that we need to compensate the difference between the true valuation and the cursed valuation in the worst scenario. And the worst scenario is the threshold, the critical point. So the constraint of exposed IR essentially saying that, oh, we need to compensate the agents according to this amount. So the seller needs to pay the bidders in the auction, even if the bidder is a loser to the auction, so may not win the item. Okay. So that gives us the cursed exposed IC and IR mechanism when we're adding the exposed individual rationality. So trying to get rid of the winner's curse. But this is kind of questionable because to avoid the winner's curse, the seller needs to compensate bidders, and the seller can actually incur revenue loss. And how bad can the revenue loss be, and can we mitigate it? So what we're showing is that if we allocate more, the seller is going to compensate more. And if the seller allocate less, if we're not allocating, then there's no winner's curse, and the seller does not need to compensate. And if we want to achieve full efficiency, meaning that we want to allocate to the individual that has the highest SI, and then the threshold is the second highest SJ. So we can construct a scenario with a reasonable valuation function and a distribution for the private signals such that the welfare of the optimal mechanism, such that the optimal welfare mechanism has the expected revenue loss that is superlinear in N, and is the number of agents, while the welfare only increases linearly in N. So this is bad. So that leads us to think about, oh, we need to make sure that the seller doesn't lose money. So we need to add a budget constraint, budget balance constraint for the seller. So if I add exposed budget balance constraint for the seller and saying that the total amount of the money collected from the participants is non-negative, what type of mechanism we can achieve? So the way we're analyzing this is that we actually consider, seems to be a strictly stronger requirement of saying that there is no positive transfer from the seller to the auction participants. And what we show is that under certain conditions of the curseness, and this condition is what we call the curseness monotonicity, which is intuitive in the sense that if other agents, private signal SJ are lower, then agent I tends to overestimate the valuation more, so which tends to be the case. Then we can show that, oh, these two are actually equivalent. So the exposed budget balance basically means the same as no positive transfer. And that allows us to design a masking operation. So the masking operation basically says that, oh, we can raise the threshold such that no curse happens, or until the upper bound where we don't have any allocation. So for example, in this figure, this is the point. Beyond that, no curse happens. And if this is the original threshold, then in the masked mechanism, we need to raise this to this masked point. So the optimal social welfare mechanism that satisfies the cursed exposed ICIR and exposed IR, and also adding the exposed budget balance mechanism, we can show that it's just, we try to do the masking operation for generalized weak rate auction. Okay.
Okay, please wrap it up because we are.
Okay, yeah. I think I need 1 more minute. I'm going to wrap it up.
1 minute.
Yeah, great.
Because
But the implication of this theorem is that, oh, if the valuation function is a max function, and then the optimal social welfare for this mechanism is really bad, it's 0. So that's really bad. But for some other families of the valuation function, so in particular, if the valuation function is a concave sum function, meaning that a concave function applying to some increasing function of the private signals, and that including most commonly considered valuation functions. So if this is the case, then we can possibly get half of the full efficiency as the number of the bidders increases. So when we have large number of bidders. And then back to the valid game. The valid game just means that we allocate the bidder to allocate to the bidder that has the higher bid, but we only allocate when other bid also exceeds 50. So the intuition is that we only allocate when the majority are all having the high valuation. Yeah, that's the most of the things I want to talk about. We also consider the revenue maximization. We have analytical solution for the optimal revenue maximization mechanism. But let me just stop here since I think I'm running out of time. And there are interesting future directions of considering more general settings, considering heterogeneous, the coarseness parameter, and also relax the exposed IC to interim IC. So I think Dirk has a paper already consider a setting for that for the when the valuation function is the max function. So let me stop here. Thank you.